First of all, thank you very much for the opportunity to talk today. I really wish I could have been there in person, but naturally that's not really feasible these days. And apologies for being a bit out of breath because I realized I'd forgotten my stylus just before the talk. So, wonderful start. Today I'm going to talk on a paper that's was joint work with Schroll and Johanna Haugland. We have a preliminary version up on the archive, but some of the things I'm going to talk about today are not yet published. There's also an archive link in the chat. Thank you, Matthew. Yes, I'm going to talk on the role of gentle algebras in higher homological algebra. Don't worry, I will try to relate it to clusters as well. So I'm going to start with a definition on the cluster tilting subcategories. And it will become clear quite early. I always want my D to be a natural number greater than or equal to 2. Nothing really interesting happens when D equal to 1. So if I have some abelian or triangulated category, and the definition works for some other cases, but for me, I'm happy with this. And I have a subcategory U of this category. Then I call U D cluster tilting if it is, first of all, functorially finite. If C is abelian, I also need it to be generating, co-generating. But my abelian categories are typically the small module categories, or the finitely generated modules, so that's not really an issue for me. And finally, and here's the big one, I need the category U to fulfill the following property. Okay, so if I have any X in C, such that there are no extensions from X to U, well, non-trivial, and those extensions can be of length from 1 to D minus 1, then I also have to have X in U. And similar the other way around. So these subsets must both be equal and they must be equal to U. This will be the big condition we're going to check today. Because the reason I'm interested in D-class subcategories, and here the higher homological part of my title comes in, is that, well, if I have if C is abelian, and I have a U that fulfills the conditions, then U is D abelian. And if C is triangulated, and I also now need to require that U is closed under shifts of D, then U is D plus 2 angulated. Now, so the reason I'm interested in the D class tilting subcategories are really because they allow us to do higher homological algebra with D abelian and D plus 2 angulated categories. These can be thought of as sort of high generalizations of categories. I will not go into details, but I will just note that the axioms for D abelian categories were given by Hasso, and the D plus 2 angulated categories were originally defined by Geis, Keller, and Opper-Plamondon. So go ask them for details, or ask me later. The other thing I would like to just mention is where these concepts come from. And here we have a little story. I'm not expert in every area of the story, so apologies if I get something wrong. But we start with cluster algebras, which you Now, it's probably most of you knew from before, and if you didn't, well, you had a school about it last week, so luckily I don't need to try to explain anything. And we noticed that cluster algebras, they better have clusters. Well, an important categorification of cluster algebras are the cluster categories. By Buan, Marsh, Reinecke, Reiten, and Todorov, 3/5 of which I believe are in the audience. And of course, their clusters are replaced by CT, cluster tilting objects. Writing cluster tilting gets old fast, so I will not do that. I'll just call them CT. Now this can be generalized to cluster tilting subcategories. I should also say that the cluster tilting objects are maximal rigid objects. And as for cluster tilting subcategories, I have one very easy trick to avoid to actually have to give you the definition. And that is I set a 2 before it. And then it turns out I actually gave you cluster tilting subcategories up there. And these are defined, for instance, for triangulated. Cats, etc. So this is how this actually relates back to cluster algebras. And the reason I care about it is because it's related to higher homological algebra. Let's also look at some examples of two cluster tilting subcategories. In this case, I will start with a path algebra type A3. This is the standard easy example. Type A3, and I have a relation, the only one I can have, really. And I observe that if I take all the projectives and injectives, there aren't that many, I get a 2 cluster tilting subcategory. And I guess it can be your homework to check that this is actually 2 cluster tilting. And there are more exotic examples in the abelian setting. Vaso categorized a lot of the type A and later radical square 0 algebras. Hus and Sande have looked at the module category over monomial algebras. So I will not go into the abelian side this time. We have some results on it, but not very relevant. But however, due to Yama, we can move a cluster tilting subcategory in the abelian category up to the derived category. So we just lift it to the derived category of the algebra by taking, well, first I take the objects in the category in the 0th position, and then I also have all D shifts. So if I can shift it by a multiple of D, then it goes into my subcategory. And here D was equal to 2, so I have all the 2 shifts, I have all the 4 shifts, and so on. You might, and this will just have to trust me or trust the Yama, perhaps more likely, that this is a 2 cluster tilting subcategory. And now one thing you might notice is that all the objects in this 2 cluster tilting subcategory end up on sort of the edges of the AR quiver of dB lambda. And that also happens if you have larger subcategories. So we thought that was a bit, or larger algebras. So we thought that was a bit odd, but then we realized, and this is shown during some homological algebra basically, that if you have a finite dimensional algebra lambda, and the U is some D-class tilting subcategory closing the shifts of D in the bounded derived category. Well, if you have a perfect complex in U, then that will fulfill that there are no non-zero morphisms from tau of that object to the object. But in the derived category, of type A at least, that just translates to, or in the AR quiver rather, that translates to being on the edge, just as we observe. So in other words, it's the outermost tau orbits where we have any hope of any action. And I know that the title of my talk says gentle algebras. This does not require your algebra to be gentle as long as it's finite dimensional. So that's just a useful tidbit that we couldn't really find in that generality anywhere. And it will become useful later in the talk. Because now we're going to talk about gentle algebras. Before I do that, let me first note, this was type A. There's a lot of nice stuff going on in type A. So that was our thought. Okay, we know that type A is a nice place to look for D-class tilting subcategories. What if I do gentle algebras? They're a generalization of type A after all. Well, first of all, the definition of gentle algebras, I won't go through that very thoroughly. I'll just point out they exist. I like to think of them as, okay, I'm the worst sort of situation I can come up in at any vertex of a gentle algebra is this with 2 arrows in, 2 arrows out. But then it's not as bad as it looks because I have relations. I need to have some relations on that vertex for that to be allowed. Most of you have probably seen the definition before, and for the rest of you, I don't think me going through it in 2 minutes will help you all that much. Another way, however, of getting a gentle algebra is to start with a marked surface. And so a marked surface, we will start with a compact oriented surface with boundary, like the disk or the torus or the annulus. And we will add a finite set of points on the boundary of the surface. And unlike other geometric models, we do not require every boundary component to have a marked point. That will be important later. Now we dissect the surface, which sounds a bit morbid, but that's just a partition of the surface so that into polygons, so that either, well, first of all, the vertices of the polygons should be on marked points. And every polygon either contains one boundary segment. So this is a perfectly fine example. Or if I happen to have an unmarked boundary segment, then I can also have an arc here. So there are none of the edges of the polygon are boundary segments, but there is an unmarked boundary component inside the polygon. But the important thing about the sections now is that we can turn them into quivers with relations. by taking as vertices the edges of the dissection, and then every time two edges in the section meet in a marked point, we add an arrow going clockwise. And these two compose to zero, two arrows compose to zero if they did not come from the same vertex or the same marked point. And the thing is, doing this, we get a quiver with relations. Quiver with relations we can turn into path algebras, because these relations have to be admissible. And the path algebra we get in that way is gentle, and we can get every gentle algebra in that way. And now that we have this marked surface corresponding to our algebra, we can take this one step further. We can use that to construct a geometric model of the gentle algebra, or of the derived category of the gentle algebra. And the first thing we do is we define a dual graph L. So that's just some graph, and I am skipping a lot of details here, such that every arc here crosses exactly one edge in the dissection. And now, the reason we're doing this is that, okay, if I want to look at the indecomposable objects in the bounded derived category, well, I know that there is a very nice description of them as so-called homotopy strings and bands. I will not go into detail on what those are. I will only say that they are in one-to-one correspondence by a paper by Opper-Plamondon-Schroll's paper to graded arcs and closed curves on the marked surface. Now, graded arcs, well, arcs in general. So first of all, I will ignore bands, I will ignore closed curves. They turn out not to be important for our purposes. But arcs, well, they can be finite, going between two marked points, or they can be infinite. That means that they start either in a marked point. Well, the important thing about them really, and I'm double checking so that Johanna doesn't yell at me because I'm drawing my spirals the wrong way. They go clockwise or anti-clockwise, depending on how we look at it, out from an unmarked boundary component, and then either to another unmarked boundary component or to a marked point. I've drawn to a marked point because drawing spirals is hard enough, let alone drawing two. So you can think of it as going towards this unmarked boundary component and then winding around it anti-clockwise. Now the finite arcs correspond to the perfect objects. Or rather the graded finite arcs, we can have a grading on this, we'll come to it in a second, correspond to perfect objects. So those are the objects that are isomorphic in the bounded derived category to a finite complex of projectives. We also have a grading on our arcs, and that's simply when we look at the dual graph L, any arc will have some intersections with L, and we define a grading. Well, the grading is really defined by taking the grading in one point, say, let's I'm graded in A, then I'm walking along my arc. I come here and I have a marked point on the left-hand side. So I go to A+1 and I continue walking. I have a marked point at the right-hand side. So the grading is reduced to on the next intersection. Anyway, point is we have a grading. It has to do with what object it corresponds to in the derived category. And yes. it's actually just defined by one grading because everything else is automatic. Grading in 1 point. Now the grading also becomes important once you want to define morphisms. So morphisms between indecomposables in the bounded derived category of a gentle algebra sound horrific. It was very helpful that Arnesen, Laking, and Pastello managed to translate that to certain maps of homotopy strings and bands. So those were the objects that I did not tell you anything about in the middle. And then they can be translated into graded intersections of graded arcs and closed curves. And this is part of where the grading comes in. It has to match up. So graded intersections, well, they can be two arcs intersecting in the interior of the surface, like this. And for there to be a map, well, if I have grading, the same grading on two crossings with a dual graph here, then I have a map between these two arcs, or rather the two objects corresponding to the arcs. Similarly, I can have a map if they meet in a marked point. And if I have two infinite objects, well, then they can, if they spiral in towards the same unmarked boundary component. Oh, yes, I forgot to mention that these gradings always have to coincide somehow. If I have two maps spiraling to the same boundary component, then we get a family of maps between these arcs, or between the corresponding objects, rather. So as you might guess, the geometric model is very powerful. It tells us a lot. Because first of all, it's about full model of the bounded derived category. So just as an example, a very useful example for us, if S is a disk, so the underlying surface is a disk, that happens if and only if lambda is derived equivalent to algebra type AN. So just looking at the surface, we can say something about what the algebra looks like. We can read of irreducible maps. We can read of AR translations. We can read of extensions, which will be very useful once you want to look for D-class tilting subcategories. And just add, there's more, but I don't have time for everything. These are just some of the things that were useful for us. So now I want to talk to you about our result. So now we get back to the D-cluster tilting subcategories. So our idea was, can we find D-cluster tilting subcategories in the bounded derived category or gentle algebras? And the answer was sort of. They definitely exist, we knew that from before. But the unfortunate thing sort of is that they end up having to be algebras, well, derived categories of algebras derived equivalent to an algebra of type AN, which were precisely the ones we knew about. Now, that was a bit upsetting, but I still feel that the way we proved it is quite exciting and shows you some of the power of the geometric model and also how to think about finding D-cluster tilting subcategories. So first of all, just recall, we're looking for categories where there are no extensions between the objects of the category and is sort of maximal with respect to that property. Now, the first thing we show, and this goes back to our first result, that the D-class tilting subcategory on the derived algebra lives on the boundary of the AR quiver. Well, that sort of happens here too. If I have perfect objects in this bounded derived category that are in, for them to be able to be in U, they have to be so-called minimal boundary arcs. there are also some restrictions on what gradings can be in there once you pick one. But yeah, so that's the first thing. So for example, this cannot be in the bounded in the decluster-tilting subcategory. Second, okay, assume I have, so this is my surface of some lambda. And assume I have some unmarked boundary components in that surface. Then we can show, we'll tell you precisely how, that there has to exist some arc, and I am going to hold counterclockwise, yay, spiraling around some unmarked boundary component, but starting in a marked point. Some such arc exists. Well, with that arc, I can, now I realize I did a mistake. Sorry, let me just quickly draw my arc because I need some more space. So some such arc exists. Well, what I do is I draw an arc that basically follows my spiral around. And the trick here is really follow it closely, and then it ends up in the neighboring point. And then that should not happen, ideally. There. And because it follows the arc, so the arc that I assume is in U so closely, we end up that this arc doesn't actually have any extensions. See, now I'm going to double check. Yes, from anything in U. So this arc must be in this subset from what we know is new. There can't be anything that intersects it. But then we get a problem because this arc, well, it's first of all, it's corresponds to a perfect object, but it's not a minimal boundary arc. You could also just point out that it has self-intersection, which gives it self-extensions. This arc really should not be in U. So we have a problem. The U that we are defining this way is not actually a decluster-tilting subcategory. That means we can't have unmarked boundary components if we want decluster-tilting subcategories. So forget about that. And in a similar way, as I am about to run out of time, we can define a similarly problematic object if I have either some marked boundary component or some hole in my surface or anything else. Those also give me trouble and means I do not get a decluster-tilting subcategory. So what I'm left with is having one boundary component and nothing interesting going on. In other words, I have a disk. And then that means that the algebra that I started with must be derived equivalent to an algebra of type AN. In other words, this is really what the decluster-tilting subcategories in the derived category of a dental algebra can look like. The dental algebra will be of type A or derived equivalent to something of type A. And then I will have this nicely spaced out summands or objects in the cluster-tilting subcategory. And with that, I believe my time is up. So thank you very much for your attention.
Thank you, Karin. Are there any questions?
Can you hear me, Karin?
Yes.
Have you thought about what happens if you pass to the universal cover of the surface first? I mean, it can become non-compact, so you end up with some kind of general category. But I wondered whether it would make sense to look for decluster-tilting subcategories there, and then project them down so that they won't be declustered tilting in the after projection, but maybe they still have some interesting structure.
That sounds really interesting. I haven't thought about it. And I can't see immediately why it would fail. So but that could work. I'm sure.
Okay, but you haven't thought about it before.
Yeah,
Okay, never mind.
I'm not.
I have a question. So in this case, there are no punctures, is that right?
I mean, the unmarked boundary components are in a way punctures.
I see. So
So
they're behaving the same kind of way.
yeah. And actually the part with the punctures or unmarked boundary components is the new part that we hope to be adding soon-ish to the archive.
Sorry, what did you say?
So the part with the unmarked boundary components or punctures, so that really corresponds to having infinite global dimension. That is the part that we hope to add, that we are writing up right now.
Okay, excellent. We should
So
look
that's
forward
not
to
a published preprint, but soon, I hope.
that. Any further questions or comments? Nothing in the chat, I think. Okay, great. Let's thank Karin for a very nice talk.